Additive manufacturing, commonly known as 3D printing, has historically relied on polymers due to their ease of processing and cost-effectiveness. However, the inherent limitations of these traditional materials have created a bottleneck in pushing manufacturing boundaries. Polymers often struggle with insufficient mechanical strength, particularly under dynamic stress or heavy loads, leading to premature part failure. Their thermal resistance is typically low, making them unsuitable for high-temperature applications where parts might soften, warp, or degrade. Furthermore, many polymers exhibit limited chemical resistance, restricting their use in harsh environments involving aggressive solvents or corrosive agents. Dimensional stability can also be an issue, as some polymers tend to absorb moisture, leading to swelling and a decrease in mechanical integrity over time. These characteristics collectively restrict additive manufacturing from producing components for demanding industrial sectors such as aerospace, automotive, and high-performance tooling. The pursuit of stronger, more durable, and more functional components has necessitated a shift beyond the capabilities of conventional polymer-based additive manufacturing. Engineers require materials that can withstand extreme temperatures, resist aggressive chemicals, and maintain structural integrity under significant stress without adding prohibitive weight. This demand is driving the exploration and integration of advanced materials into 3D printing processes. The expansion of additive manufacturing into critical applications is now being enabled by a new class of materials that overcome these polymer-centric challenges. These advanced materials, encompassing sophisticated metals, high-performance ceramics, and engineered composites, offer properties that redefine what is achievable with 3D printing, moving it from prototyping to end-use production. One such transformative material class is high-performance metal alloys. Unlike their polymer counterparts, metals offer superior strength, hardness, and thermal resistance, making them indispensable for structural applications. Additive manufacturing with metals, often using processes like laser powder bed fusion, allows for the creation of intricate geometries and internal lattice structures previously impossible to achieve with traditional methods. Consider titanium alloys, a prime example of high-performance metals in 3D printing. These alloys possess an exceptional strength-to-weight ratio and outstanding corrosion resistance, along with biocompatibility. Their ability to retain strength at elevated temperatures is crucial for components operating in high-stress, high-heat environments. In aerospace, 3D printed titanium components are used for lightweight aircraft structures, engine components like turbine blades, and satellite brackets, leading to significant weight reduction and improved fuel efficiency. The medical field utilizes titanium for customized implants and prosthetics, leveraging its biocompatibility and the ability to create patient-specific designs. While metals address many mechanical and thermal limitations, certain applications demand even greater hardness, chemical inertness, and electrical insulation. This necessitates the adoption of advanced technical ceramics in additive manufacturing. These materials retain their integrity in conditions where metals might corrode or deform. Technical ceramics, such as Alumina and Zirconia, are notable for their extreme hardness, high melting points exceeding 2000 degrees Celsius, and excellent resistance to wear and chemical attack. Alumina, for instance, is highly resistant to thermal shock and corrosion, acting as an effective electrical insulator. Zirconia offers outstanding mechanical properties at both low and high temperatures, along with chemical inertness and resistance to attack by metals. Applications for 3D printed ceramics include critical parts for electronics, such as microelectronic substrates and insulators, where electrical stability at high temperatures is paramount. In industrial settings, they are used for wear-resistant components and tooling, while in the medical field, biocompatible ceramic implants like dental prostheses are becoming more common. A third category of materials enhancing 3D printing capabilities comprises advanced polymer composites. These materials bridge the gap between pure polymers and other high-performance materials by integrating reinforcing fibers or particles within a polymer matrix to significantly enhance mechanical, thermal, and chemical properties that traditional polymers lack. Continuous fiber-reinforced polymer composites, particularly those using carbon fiber, offer a compelling balance of lightweight design and high structural performance. Carbon fibers provide exceptional tensile strength and stiffness, chemical resistance, and temperature tolerance, transforming what a polymer-based part can achieve. These advanced composites find application in high-stress, weight-critical environments. For example, in the automotive industry, they are used for lightweight structural components in race cars, while in sports equipment, they enable the creation of high-performance gear with enhanced durability. The ability to precisely orient these fibers during printing allows for tailoring mechanical properties to specific load paths. The integration of these advanced materials is fundamentally changing the landscape of additive manufacturing. It enables the production of parts with complex geometries and previously unattainable performance characteristics, pushing beyond the traditional limitations of prototyping into functional, end-use components across diverse industries. This shift is expanding design freedom, reducing lead times, and facilitating the creation of bespoke solutions for demanding technical challenges. Ultimately, the drive to overcome the physical constraints of conventional materials is transforming 3D printing from a niche technology into a versatile manufacturing method capable of producing high-performance, durable components for a wide array of industrial applications.